Design of concrete structures, chapter 4, flexural analysis and design of beams, example 1. So in this example, we do have a rectangular cross section with dimension of 10 inches in width and 25 in height, with the effective depth of 23 inches, and consists of a concrete block and three a number 8 rebars, steel rebars. A concrete has a compressive strength F prime C of 3600 pound square inches and a tensile strength in bending for modulus of rupture Fr is 475 psi. The yield point of steel Fy is 60,000, and we want to calculate or determine the tensile and compressive stresses in both concrete and steel. If a bending moment of 45 feet times kilopounds applied to the cross section. So let's see how that goes. First of all, we do know, or based off the problem statement, that the modulus of elasticity for steel is 29,000 kilopound square inches, and the modulus of elasticity of concrete is 3600 ksi. Number 8 bars, steel rebars has an area of 0.79 inches square. If you copy the table for rebars and their specification in either the book or codes, and because we do have three of them, so AS is 3 times the cross-sectional area of each of those steel rebars. So the total area is 2.37 inches squared for the all rebars. The next step is to convert the steel rebars to an equivalent concrete to have a unified or a unique uh, cross sections, and all in concrete. So N is a conversion factor of modulus of elasticity of steel, which is the higher modulus material, to the concrete, which is 29 over 3.6 is almost, it gives us a numeric value of 8.05, and just go by n, the number n is equal to 8, and a prime, which is the equivalent cross section, is a prime, which is n times as, and it just gives us a prime, because we have to subtract the one of those from the whole cross section. We have to take those rebars out of the concrete, and there is a hole, so we need to subtract one of them, one of those n, one of those conversion, because of the effect of these three elements. So that's n minus 1 times as, that's 8 minus 1, 7 times total area of 2.37, that's 16.59 inches squared. That's the converted total area of steel rebars to equivalent area of concrete. Next step is to see which stage of stress and strength in flexural analysis design or cross section is at. So we just assume we are in the very first category, which is the stress elastic and section uncracked. So we have intact cross section. We just assume that FCT, a stress in concrete in tensile part, is smaller than modulus of fracture, which is provided to be 475 psi, and then we verify it. So let's proceed. That's the easiest analysis. So the very first stage is to calculate the y bar from the top of the section. So that's summation of ai times yi times over summation of areas. So summation of area is simply 10 times 25, which is 250 for the block itself, and 60.59 for the equivalent, these two part, which is the effect of conversion of steel rebars to equivalent concrete part, That's 6 plus 16.59, and likewise a 25 times 10 times the cross section, the centroid for the first part, which is if the total area of concrete is 20, height is 25, the centroid is half of the center, plus 16.59, the centroid of the equivalent section to the top, which is 23 over the area, and it just gives us y bar is equal to 13.15 inches squared. That's our centroid for the overall entire cross section. And just if we just consider that to be y bar equal to 13.2 inches squared, that's inches squared, my bad. That should be, that's the, no, that's inch, that's distances. No, that's correct. So I just modified this part. That's the distance from the top of the section, so that's simply in dimension of that. And m, if we just convert the bending moment in problem statement, which is 45 feet times kilopounds, it just gives us a conversion times 12 times 1000, it just gives us 540,000 inch pounds. That's the conversion to from feet kilopounds to inch pounds. And at the same time, we do know stress is mc over I for concrete and for steel at the same time. So m and I moment and second moment of inertia remains the same for both of them, and the distance for concrete is they just measured from their centroid. So that's 13.2 minus to 12.5, which is the distance of centroid of the overall cross section minus the centroid of just the concrete. That gives us 0.7 for compressive concrete, and for steel that's 23, that's 23 minus 13.2, which is y bar from the top, and that gives us this distance centroid of equivalent uh, concrete of steel to the centroid, that's 9.8. And we need to calculate the moment of inertia or second moment of the area. So moment of inertia of the overall cross section consists of two parts, which is I concrete, I steel, I equivalent I of steel, which is again a second part of concrete. So that's a, for the concrete block, that's simply enough 112 base cube height plus AD squared for concrete part, and then again I steel plus AD squared for concrete for steel. But if you pay attention, I steel, I for moment of inertia for steel, it's relatively small and it's almost close to zero because of the small area of a small equivalent area of steel rebars in comparison to the large area of concrete. Yet a concrete is a 112 base cube height, and cube height is a 25. You can see how large would be that number in terms of this small area when in revolution about x-axis. That's something like barely that even we can ignore it in different ways. So that's almost zero. But AD squared in terms of the distance to the centroid is and that's a squared of that. That's a we can consider that part. So for the concrete part, if you replace that, that's 112 base, which is bits base cube height. Cube height is 25 inches, and cubed is 25 to the power of a 3 plus AD squared. We already calculate the what is distance of D, which is 13.2 minus 12.5 times A of concrete block, which is 250 plus AD squared for equivalent rebars area to the concrete, which is 16.59 times a 3 minus a 13.2, which is this distance, and then a squared. And if you just do the math, it just gives us a moment of inertia equal to 14,736.69 inch to the power of 4. And if we want to calculate stress in concrete and steel rebars for both materials right now, we have Fc, that's mc over I, and Fs mc over I, and different distances. So M is a 540,000 inch-pounds and I is almost 14,000. So let's go to the concrete. So compressive stress in concrete part. So that's definitely the top of the section, which a compressive part of the section, and that's FCC. That's the M, which is this amount in inch-pounds, times C, which is the distance of centroid from the top of the section, because we are talking about this part, over the moment of inertia, which is this amount in inch to the fourth. And if you calculate it, it's 483.69 pound over inch squared, and that's from calculated from this distance. So that's the distance from the top of the section to the neutral line or neutral axis, and that's simply FCC stand for stress in first C stand for concrete and second C stand for compressive. So compressive stress in concrete is equal to almost 484 pound square inches. And the important part is, because the section remains uncracked due to our assumption, we also have concrete at tension part. So cross section doesn't breaks into two parts. So we also do have a concrete part below the uh, neutral line, neutral axis or central. So in that case, FCT, we do have a tensile concrete, which is shown here, and that's a stress for concrete in tensile part, and that's again MC over I, and I this time is a all the way down to the cross section for concrete block, and that's again if you subtract a 13.2 from 25, and it just simply gives you a 11.8, which is the distance of a compressive tensile concrete, and that gives you a FCT equal to 432 pounds square inches. That's for tensile stress in concrete, and yet we have to review the tensile stress in uh, uh, let's review the tensile stress in concrete. So we first make the assumption of we have a first scenario, which is the elastic domain and an uncracked section, and that's if FCT, if a stress in concrete, in tensile concrete, is less than modulus of fracture. That's our condition, which we also reviewed in previous video, which is FCT is equal to 432, and that's definitely below 455. So our assumption is correct, and there is no tension cracks in our concrete. So our uncracked transform section is verified once more. So the assumption was correct, and let's go to tensile stress in steel rebars. Now we are done with the concrete part. Let's go to tensile stress in steel rebars. So MCI, and that's 9.8, which is a 23 minus 13.8, 13.2, which is the Y bar, and that gives us 9.8 for the centroid of equivalent a concrete, which replaced instead of rebars, and that gives us over the same moment of inertia. It just gives us a 359.11 pound inch square. And if you just remember Fs total stress in steel for the total, because we have a equivalent area for that, so we have to multiply the N, which is ES over E6. So this Fs This one is calculated based off of the equivalent of the concrete. Now we need to multiply that by 8, which is the conversion modulus of steel to concrete, because we definitely do know that the steel stress is much higher than an equivalent of concrete. So that gives us a equivalent of that 8 times 359 point almost 11, that's 2872.88 psi. So if we want to wrap up the conclusion, for concrete we do have compressive concrete, we do have tensile concrete, because we have an elastic section, an elastic domain of uncracked section. So that's why we do have two-part compressive stress and compressive concrete, and also tensile concrete, and FC is equal to 484. That's FCC, concrete compression. That's FCC. That's FCT, tensile concrete stress, 432. And also we do have a steel rebars, which has a total stress of steel is 2873 psi. Thank you. We'll solve a more problem and discuss more about the flexural analysis in next videos. Thank you.